Hello, I just wanted to make a very, very quick note at the start of this video to say I was a complete idiot and decided to take my jumper off about 2 minutes in, which was perfectly reasonable as it was quite hot. However, I didn't take my clip-on microphone off and change it to my shirt. So the first 2 minutes of audio are perfectly fine. The remaining 1 hour and 28 or whatever is quite bad. So apologies for that.
Okay, let's get started. Well, nice to see so many of you here. My name is Rob. I'm a particle cosmologist, mostly based at Royal Holloway, University of London. And I want to talk today about cosmology. Sorry? Oh, no, that's good. Yeah, this is good. Yeah.
Brilliant.
So we're going to talk... Thank you. So we're going to talk today about cosmology. Now, cosmology, I'll talk in a moment about what cosmology actually is, because it's perhaps not a word you're as familiar with. You know, astronomy, we kind of know what astronomy is about. Cosmology is a little bit broader and a little bit larger scale. So for an overview, first of all, we're going to go through some preliminaries. So I'm going to give you all a little bit of a maths lesson, first of all. Then we're going to spend quite a long time talking about the Big Bang and the first 10 seconds of the universe. So when the universe was still very young and hot and dynamic. We're then going to zoom out a little bit and start with where we are now in the Beecroft Gallery and zoom out onto the largest possible scale we can and discuss our address in space. If we were to write down, for some other civilization to post us a letter, what would be the lines of our address we would include? Then we're going to come back and talk about something called dark energy. We'll only talk about this quite briefly because, frankly, nobody knows very much about it, so there's only so much you can say. And then I want to talk a little bit about science in general and what it means to be a scientist in our society. And there'll be lots of time for questions too. Well, hopefully lots of time. But if any really urgent questions pop up as I'm going, do feel free to put your hand up. Okay, so preliminary things. I'm going to talk about what is cosmology, first of all. I'm then going to talk about how we represent very big and very small numbers, because we will be using a lot of very big and also a lot of very small numbers. I then want to talk about distances, specifically light years, what these mean. And then we're going to talk briefly about matter and antimatter. Okay. So first of all, what is cosmology? Cosmology is about studying the universe on the largest possible scales. So, astrophysicists look at individual stars, individual galaxies, which are still obviously extremely large. Cosmologists try to look at the whole universe in its entirety as one single system. Now, this often involves looking at things on a very large scale, but actually it also involves looking at things on a very small scale. So part of my research as a particle cosmologist is about understanding how the subatomic world, particularly the subatomic world in the very early universe, informs the way that the universe is on the very largest scales today. So this image here, by the way, is an image taken from the Hubble telescope, its ultra-deep field. So this shows about 10,000 galaxies in an area of the night sky that's about 1/10 of the size of a full moon. So a very small patch of sky, but an enormous number of galaxies. Okay, I'm going to take my jumper off because it's so hot in here. Okay. I'm also going to open that door a bit more. Can anyone still see the screen? It's a little bit washed out. Is that okay? Yeah? Okay. Super. Okay. So, very big numbers. Because we're talking about the universe as a whole on the largest possible scales, we have to know how to write down very large numbers in quite a concise way. So, for example, if you have the number 1 million, as you hopefully all know, this is a 1 followed by 6 zeros. Okay? If you want to write this in a much more compact way, you can put the 1, which is the front of 1 million, and then multiply it by 10 raised to the power of the number of zeros. Okay? This is a shorthand notation for writing extremely large numbers. Another example, 6.2 billion. A billion, 1 billion is a 1 followed by 9 zeros, so there are 9 jumps to the right of the decimal point. So you can write this 6 with 9 jumps to the right, 6.2 billion, as 6.2, and then times 10 to the power of 9 because there are 9 jumps. Okay? So basically, if you see a number written like this while I'm talking, which has a power on 10, just imagine that number of zeros following the end of the decimal point. Okay? So 10 to the 9, 9 zeros. Okay? Similarly, very small numbers we will have to talk about. So 1 million is 0.00001, so 6 zeros in total, but on the left-hand side of the first digit. And we write this in a similar way, but as a negative 6. Okay? So if you see a number like 6.2 times 10 to the negative 4, you just imagine that the decimal place is 4 jumps to the left of where I put it in the first place. So, for example, when we're talking about the early universe, we're going to be discussing timescales that are on the order of 10 to the negative 40 seconds. So this would be 0.000 with 40 zeros and then a 1. Okay? So still unimaginably small times, but written in a slightly more easy to read way. Okay? Okay. Distances. So I'm sure you've all heard the term light year. Perhaps quite confusingly, as this has the word year in it, you might think this is a duration of time, but actually it's a unit of length. So specifically, it's defined as how far light travels in a single year. Light is extremely fast. Light is the fastest thing there is in the universe, traveling at about 300 million meters per second, or about 190,000 miles per hour. So in 1 year, it travels an extremely large distance. Okay? If you work this out, you can take the speed of the light, times it by the number of seconds in a year, and you get about 590 billion miles. So light year is a convenient unit for us to use because most distances in cosmology and in astrophysics are very many billions of miles, so we write them instead as a number of light years, which is a lot more compact. Okay? Okay. A slightly less common unit is the light minute. This is a neat one just because it takes about 8 minutes for light from the sun to reach us. And so one way we can express the distance between the sun and the earth is at a distance of 8 light minutes. Okay? How far light travels in 8 minutes. That also means, because the sun is quite far away from us, not extremely far, but it means, for example, if the sun was just to suddenly disappear completely without a trace, it would take us 8 minutes to know. So not only would we not see it for 8 minutes because it takes the light that long to reach us, it also takes the gravity that long to reach us. So we would continue orbiting as usual for another 8 minutes and then spin off and fly off into space. Okay? Next, I want to talk about matter and antimatter. So this is my research area, particle physics. So matter is just another word for stuff. Okay, it's stuff that has mass. It has a weight. If you were to put it on a scale, you could see how much it would weigh. Antimatter, although this sounds sort of quite exotic, and in many ways it is, it's really just another kind of matter. So it still has weight. It still has a mass. But some of the properties are inverted. So, for example, if an electron has a negative charge, a positron, the anti-version of an electron, has a positive charge. So the numbers are just sort of swapped around, okay? But it still weighs something. And if you want to hear more about particle physics and quantum theory, I'm talking about this next week at the same time in this room, okay? So this diagram here, this is the standard model of particle physics. So it's the most thorough and more or less correct model we have of all of the stuff there is in the universe. So if you've done any chemistry, we have the periodic table, which has all the different elements, hydrogen, oxygen, neon, etc., etc. And you might also know that all of these things are made up of the same basic 3 components. So there's a nucleus to the atom, which is made of protons and neutrons. And then orbiting around the nucleus, there are the electrons. So there are three kinds of particles that make up all of these things. Now, there's a lot more particles here than just those three. If you want to build all of the matter we see in this room on our planet, in the stars in the galaxy that we can see, crucially, you only need three of these. You need these two, what are called quarks up here, the up and down variety, and you need one electron. So the up and down quarks, they combine to make protons and neutrons, and the electrons then spiral around in the atom, okay? But there's a lot more stuff here. So, when chemists say, we are the central science, we study what matter is made of, well, actually, you only study a tiny fraction of what matter is made of. There's a lot more to it. All of these different quarks, the other leptons, and so on. So particle physics, the standard model, it looks a little bit like the periodic table. It is like the periodic table of particle physics, but there's a lot more going on. There are these so-called gauge bosons here which carry forces. So not only do particle physicists care about describing matter in its most fundamental form, we care about describing the interactions of matter in their most fundamental form, which means talking about forces. But I'll talk much more about that next week. So, as I say, matter and antimatter, these have the same weight. So here is an electron, here is an anti-electron, the positron. It will have certain properties reversed, such as charge, and a couple of others that are a little bit more technical. So in some sense, you can think of the positron as a little bit like the electron's evil twin. Okay, it's not really evil. It's just as happy to be matter as the electron is. But the reason it's slightly evil is that when these things collide, there's quite a cataclysmic release of energy. So these particles will annihilate. They will disappear. You'll have no more matter, no more antimatter, but a large amount of energy released. Okay. So we will come back to this idea later. The Big Bang. So the Big Bang happened about 13.8 billion years ago, we think. And in this moment, this instant in time, all of the energy and all of the matter and all of the space and all of the time that will ever exist in the universe was created. So this is, the moment where the universe began, okay? It's not a point in space, interestingly. It is a moment in time, because prior to the Big Bang, there is no space, okay? It is where all of the space comes from. All of the energy content that will ever exist in the universe, similarly, comes from at this point, okay? Now, that's quite a big idea, just to start on. So we're going to break this down into three things. We're going to talk, first of all, about this moment, this instant of the Big Bang itself, which is what is known as a space-time singularity. We're going to talk about some of the evidence for the Big Bang, and then we're going to talk about how the Big Bang sort of happened. Well, let me rephrase that. We're not going to talk about how the Big Bang happened, because we can't talk about that. We're going to talk about what happened very shortly after the Big Bang, because, as you'll see in a moment, we can't go directly back to the Big Bang in our understanding. Okay, so the moment of the Big Bang is what we describe as a space-time singularity. So the only other place we know of that we find space-time singularities in the universe is at the center of a black hole. Of every black hole, there is a space-time singularity. This term singularity is borrowed from mathematicians. In mathematics, it's a point where your equations lead to something nonsensical, like division by zero. 1 divided by 0 is not a mathematical operation we can do. Because how do you fit 0 things into one thing? Well, you could have it, it can fit in infinitely many ways, right? There's no sensible answer to this equation. In fact, there's a nice quote by, I think this guy is a comedian actually, not a physicist, but he says, black holes are where God divided by 0, which I always think is quite a nice quote. So singularities, physically, are points of infinite density. So a point where a very large amount of matter, in the case of the Big Bang singularity, all the matter that will ever exist in the universe, or can exist in the universe, is condensed to a single point, which has 0 size, okay? Leading us to a point of infinite density. And I'm going to talk more about black holes on the 25th of May. Again, I'm shamelessly plugging. So, why are space-time singularities hard to understand? So this is a recycled slide from another talk I gave a few weeks ago. the reason singularities are hard to describe is that they straddle this very uncomfortable position between the two fundamental theories of 20th century physics and 21st century physics. So there are two theories on which modern physics is based. There is quantum mechanics, which is the way we understand the sort of microscopic world, the world of subatomic particles, of atoms, molecules, very tiny things, okay? And then there is general relativity, which is Einstein's theory of gravity. This is how we understand the way the galaxy spins, and we use it to talk about the orbits of planets around the sun, and it predicts the existence of black holes. Now, singularities are difficult because a space-time singularity, as I've described it, remember, something very, very heavy squashed down to a tiny point, is both very small, meaning you want to think about quantum mechanics because quantum mechanics is how we deal with very tiny things, but it's also very, very heavy, and general relativity is what we have to use for very heavy things like stars and like galaxies. And in the middle of this very difficult intersection is something called quantum gravity, which we don't have. We don't have the equations of quantum gravity. But if you wanted to understand what's going on at the center of a black hole, or what's going on at the very beginning of the universe, right up to the point of the Big Bang, you would have to have these equations in order to study that, because it is both very heavy and very tiny. Okay? And another nice quote, now this guy is a physicist, so if black holes are where God is dividing by zero, then quantum gravity is where these mathematical singularities, whether of human or divine origin, are resolved. Because sometimes a singularity in mathematics is not a case of there's something being really deeply wrong. Sometimes it's just we're calculating things wrong. So whether these singularities are human, as in we're making a mistake, we don't know the full picture in our mathematics, or there really are singularities there, quantum gravity will tell us the answer. Okay. Before we move on, I just wanted to see if there are any questions just at this point as we're going through. No? Okay. Then we've got some more time. So, the Big Bang. We're going to talk now a little bit more about the evidence for the Big Bang. So, it starts off really in 1915 when Albert Einstein publishes his theory of gravity, general relativity. But a few years later, this guy here, Alexander Friedmann, about 7 years later in 1922, publishes this equation up here, which is now called the Friedmann equation. So what Friedmann has done is he's taken Einstein's equation for gravity. I should talk a little bit more about what Einstein's equation for gravity is, or what it says. So prior to Einstein, in the 17th century, Newton writes down his first equation for gravity, where he says, any two objects that have mass, remember matter is stuff with mass, will attract one another, and they will attract with a force. We call this the gravitational force, where, if you have heavier things, they attract more strongly. That's why if you go and stand on Jupiter, Jupiter is pulling you down into its, doesn't really have a surface, but it's squashing you down more than it is on the Earth. And it also depends on how far away the objects are. So it's an equation for how strong the gravitational pull is between two heavy objects. Einstein comes along in 1915, and following on from work he had done in the previous decade on relativity, where he's thinking about time and space and light, and he publishes his theory of gravity, in which no longer is gravity considered a force between two masses. It's considered as the tendency of objects to follow paths in curved space-time. So a heavy object like the sun bends space-time inwards. It's like putting a bowling ball in the middle of a trampoline. It bends space in towards it, and lighter objects that are sort of pushed and put around the edge of the trampoline will follow the curvature, the dent in space the sun makes, and move towards it. So there's it appears to be a force. It looks like a force because things are moving, but according to Einstein, it's not a force. It's curvature of the fabric of the universe. Okay. So Friedmann takes Einstein's formulae that he has, and he reaches this equation. And this is quite a neat equation. What I've done here is I've labelled where some of the different terms in this equation come from, just to show the way that science works. It's, it's not just one guy or one woman working on something and, coming up with these things out of nowhere. It's such a trans-temporal progression of ideas from, generations and centuries and even millennia. So in this equation, you have pi, which is, nearly 4,000 years old, dates back to ancient Babylon. You have Newton's constant of gravity, big G, this goes back to the 17th century in England. And then you've got the speed of light, which goes back to 17th century Denmark, where this is first measured. So lots of different cultures and time periods are coming into this one equation here. And the most curious term is this one I've highlighted in red here, which Einstein called his cosmological constant. And we will talk more about that later. But this is something Einstein added essentially because he didn't believe in the expansion of the universe. He didn't believe in the Big Bang. And in order to stop his equations predicting the Big Bang and predicting the expansion of the universe, he added in this fudge factor here, which is a thing physicists often do when we don't trust what our equations are telling us. But as I say, we'll come back to this. So Friedmann's equation shows that mathematically it is possible for the universe to change in size. It might grow or it might shrink, depending on how much stuff there is. If you have a universe that has a lot of matter, this matter will attract gravitationally and will sort of try to squash the universe down. It will slow its expansion. If you have a very empty universe with not much matter, it will grow at a very quick rate because there's no gravity pulling things back in. So prior to Friedmann's equation, it was assumed that the universe was not changing in size. So the model was the so-called steady-state model, which was sort of most championed by a very famous British astronomer, Fred Hoyle, stated that the universe pretty much stays at its current size. New matter can appear. It's sort of generated at the edges to fill in the gaps where it drifts apart to keep the density about the same. And this was the consensus for quite a long time, really until the 1960s. Okay. So Friedmann's equations tell us it's possible for the universe to expand, but the scientific consensus is that the universe is not expanding. So who is right? Is the universe expanding or is it not expanding? So coming back to this cosmological constant, as I say, this is something Einstein added into his equations to prevent the universe from expanding. Okay? His equations seem to naturally imply that the universe must grow. It can't stay at the same size. And he later called this his biggest blunder because, as we will see shortly, it turns out the universe is growing. So he had added this term in for no good reason. But Einstein, being a pretty smart guy, he wasn't actually completely wrong. This cosmological constant is quite an important thing that has had a sort of reinterpretation with modern physics. So even when Einstein's wrong, he's not really wrong. Any questions at this point, just before I talk on? Yeah?
You were saying about the Friedmann equation
Yeah.
and how it uses things from the past, like ancient Babylon.
Yeah.
Do you think there's going to be more stuff added to it in the future as we go on?
Oh,
Or
yeah.
is that going to stay the same now?
Well, the Friedmann equation is just using Einstein's theory. It doesn't have any quantum mechanics in it. So it's quite good for when the universe is fairly old. Because at the moment, the universe, with it being a very big place, it doesn't have too much matter concentrated in any one space. It's sort of fairly empty. Space is quite empty. So this equation works pretty well because there aren't any super high densities. But it doesn't work when you're talking about singularities, certainly. It doesn't model the collapse of matter very well, or the expansion of the universe if you go too far back in time, because then there's too much stuff around. So if you were to have an equation that would be, the sort of quantum gravity version of Friedmann's equation, which takes you right the way back to the Big Bang, there'll be all sorts of stuff here. I can't even imagine all sorts of stuff. Okay? Yeah, that's a great question. Anything else? No? Okay, good. So, okay. So, a couple of years later, so remember 1922, Friedman has his equation that talks about the universe might expand, the universe might contract, it can, sort of do anything in between. It might grow, it might shrink, or it might stay the same. But it leaves open the possibility that it could grow. 7 years later, 1929, the American astronomer Edwin Hubble publishes data from astronomical observations he's made of different galaxies, very distant galaxies, that galaxies are receding away from us. Generally speaking, if you look at a distant galaxy in the night sky and you measure by looking at the light coming from it, there's a technique for doing this, which way it's moving. Is it moving towards us? Is it moving away from us? Generally speaking, most are moving away from us, okay? Which would tend to suggest things are expanding, okay? If everywhere we look, we see galaxies receding away from us, it suggests things are expanding. But not only are they all moving away, the further away they are, the faster they are moving away. So the further away a galaxy is, the more quickly it is receding away from us. Which sort of suggests, if you think about a balloon with little galaxies populated on the surface of the balloon, as this thing expands, the further away 2 points are on this balloon, the faster they will move away from each other as the balloon expands. Because every little section of space between the two galaxies is expanding itself. So this part here and this part here that are initially very far apart, they become even further apart as the balloon grows compared to, say, 2 points that are closer together. Because if there's more initial space in between them and all that space is expanding, they will move further apart the further away they begin. Sorry, let me say that again. They will move apart more quickly the further apart they begin. Okay? Because there's more space expanding between them. Hopefully that makes some sense. A couple of years later, Georges Lemaitre, in 1931, suggests actually the Big Bang. He doesn't call it the Big Bang. He says that the universe might well have begun from a single point that he calls the primeval atom. And interestingly, he was actually a Catholic priest. So I often think of him as the Catholic Church's apology for what they did to Galileo, to cosmologists. So he suggests that the universe begins from a point that he calls the primeval atom. Several years later, a couple of decades later, in fact, in 1964, Penzias and Wilson, these guys here, while working at the Bell Labs in New Jersey, doing something completely unrelated to cosmology, detect a homogeneous background of microwave radiation. So what do I mean by that? I mean, whichever direction they look in, whether they're looking north, south, left or right, whichever way they look, they find a sort of echo of microwave radiation. Now this microwave radiation, we now call this the cosmic microwave background radiation, is the sort of echo left behind by the very hot Big Bang. So all of the steady state models, which say the universe has always been, has been there the whole time, basically in its current state, at its current size, don't make any prediction of this microwave background. Only the Big Bang predicts this. So this is like the smoking gun of the Big Bang left over from this very, very hot period immediately after the Big Bang that has cooled as the universe grows and has stretched out this radiation into microwaves that these two guys detected and both won the Nobel Prize for as a result. A couple of years later, Hawking and Penrose put the sort of final, well, I don't want to say nail in the coffin because actually it's proving the Big Bang, but they fill in the last piece of the jigsaw that supports the Big Bang by showing mathematically that the universe must have begun with a singularity. If the universe is expanding, as we know it is, thanks to Hubble's observation, then it must have started at a point at one moment in time. Now, I mean, this seems fairly obvious. It feels like, well, why did it take Hawking and Penrose to come up with this? Because surely, if everything is growing, everything is moving away, if you reverse time and trace it back, it must have started out smaller in the past. And if you trace it back really far, it must have started out, everything would have been on top of itself, right? If everything is receding away from a single point, early on in the universe it should have all been on top of everything else. But this idea is a little bit more complex and it needs some mathematical proof to it. So Hawking and Penrose are kind of doing the maths, showing that the universe must have begun with a singularity. Okay? And so the Big Bang is science. You know, we detect that galaxies are moving away from each other very quickly. The further apart they are, the quicker they move away from one another. This suggests space is expanding. And when we trace this back, when Hawking and Penrose do the math, we know it must start with a hot singularity. Okay? Yeah.
What is the evidence that the universe is expanding again? I'm
Yeah.
clear on that.
So
Because,
this is
we're only here a short time,
Yeah.
and to know the universe is expanding, surely you need a long period. So what things do they use to say gives us evidence?
right. Yeah. So you can do it without just looking at it at two different times. You can look at it just in one instant, because you know if we look at galaxies up in the night sky, we see that all of them are moving away from us. Whether you look, you know, if you're in Australia and you're looking in the southern hemisphere, those galaxies are moving away from us. The galaxies above us in the northern hemisphere, they're moving away from us as well. So everything appears to be moving away from the Earth. Okay. Now that doesn't mean that the Earth is the center of the universe,
No.
because you might, you know, conclude that if you were perhaps an astronomer from a few hundred years ago, that if everything is moving away from the Earth, surely the Earth is the center of the universe, and everything's going away from us. But actually, if you were to sit on any one of these planets, that, you know, in the galaxies we're looking at, moving away from us, they would see the same thing. They would see everything moving away from them too. So the analogy that's often given is, it's like if you're making raisin bread or something. You know, you have little raisins dotted throughout the dough. The dough expands in all directions, so every raisin is moving away from every other single raisin. So there's no single common center to the universe that everything is expanding away from. Every point is expanding from every other point. So it's because we can see how fast the other galaxies are moving away, we know they're expanding from us, and we know they're expanding from each other, so we know the whole universe is growing, is expanding. Okay. Does that make sense?
I still don't understand what evidence they're using to see that expansion.
So they're using
Sorry.
something called the redshift of the galaxies.
Right.
So there's a phenomena that, you know, if an ambulance drives past you, you notice it goes, as it's going past you, and as it's coming towards you, it goes, so the frequency increases. So light has the same effect, where if you see if you have what sort of orangey light, if something like our sun, which makes sort of orangey light, was to move away from us very quickly, that light would change color and become redder, because the wavelength would be stretched. Or if it was to rush towards us, it would compress the wavelength and it would become bluer. So when we look at the galaxies, we see more of them are red than are blue, which tells us more of them are moving away from us than are moving towards us. So that's the evidence set. Okay? Yeah?
I still don't get it.
Join the club.
I know. No, but it's like, what if instead of expanding,
Yeah.
it's a huge space
Yeah.
that keeps actually moving and dancing around, and it feels like the galaxies are moving away from us. They're just moving within a contained space still, rather than expanding infinitely.
So like they're filling out to the edge of something.
Yeah, let's say we have a huge square out there,
Right.
and the galaxies keep moving around. It feels like they are expanding,
Yeah.
just because we do not see the edges of that big square.
Well, they might-
Instead of just expanding the universe,
Mm.
the universe is there.
Moving around.
Yeah,
Stuff
moving
is
around
happening.
us, because they are so far apart, feels like they are, the universe is expanding, but they're just moving. Whoa, it is big round, big square. So that's the bit I don't understand, how it
Yeah.
proves the universe is expanding, or maybe we feel it's expanding, but it can be also like
Yeah.
finite space.
I mean, we can't. What we can't do, and there's a fundamental reason we can't do this, which is part of Einstein's theory. I can't label this point here as point A in space and this point here as point B in space, because I can't keep track of something as abstract as space. We have to look at the stuff in the space. You're quite right. So we look at the galaxies. We see the galaxies are moving away from each other, and we interpret that to mean the universe as a whole is growing. But what does it actually mean to say, is space growing? Is it just the distance between the galaxies is increasing? Does that mean the space between them is growing? Well, because of Hubble's observation that the further apart they are, the more fast they are growing. tells us that if there's more space in between them, there's a quicker expansion. So that would tend to imply that it's not just that they're all moving away from a common centre at the same speed. The points that have more space in between them are expanding quicker, which tells us there's something in between them that is growing, not just they're moving away sort of on their own. So
I understand that view,
Yeah.
but still that can be contained within
It could be,
infinite
yeah.
space after a huge,
Yeah.
something that my mind
Yeah,
can't
so
comprehend or whatever.
no, well, that's quite right. So there's, the question of the global geometry, the global structure of the universe is not something we know much about. There are some models that would make some observational differences. Say if the universe is closed in shape, like for example, we're living on the surface of a higher dimensional sphere, as opposed to a higher dimensional hyperboloid, like a Pringle shape. There are some observational differences between those two possibilities. So there are things we can do to constrain the kind of global structure of space, but the problem is that the measurements we're making put it on such a knife edge that we might be on a closed shape, like a sort of spherical global shape to the universe, or it might be a curved, negatively curved shape like a Pringle. So we don't know if we live on a Pringle or a Malteser, basically. It's one or the other. Yeah?
How do they know that the redshift of the light that's travelling at a distance is actually because of the expanding in space?
And not just redshift.
Are there any other theories? I'm thinking of the Newton's laws of published that light travelling a further distance has lost energy or something like that.
Right. Yeah, so there are some assumptions in cosmology, certainly. One of the assumptions is that the laws of physics here are the same as the laws of physics anywhere else in the universe. So if light travels at a certain speed on the Earth, it travels at the same speed in the Andromeda galaxy, and so on. Now, there are some theories that talk about Lorentz invariance violation, which basically means the speed of light would be different at different places in the universe. None of these have any evidence. Some people, they play with them and see what comes out, but they're not really seriously considered.
Yeah.
Generally speaking, it's a principle we stick to, that the laws of physics here are the same as the laws of physics there. There could be differences, but we haven't found evidence yet. Okay. Any other questions? One more, perhaps? Yeah.
If the cosmos as we have it now is all a result of the Big Bang,
Yeah.
and all the matter and antimatter, what was this singularity point suspended in before this occurred? And what was the cosmos beforehand?
I can't answer that. I can't answer it. So it's a really good question. I mean, it's one that keeps us all up at night as physicists. But the reason we can't answer it is, again, because of this fact that if you go back to the Big Bang itself, to this space-time singularity, you need a set of equations that we don't yet know. And if I did know them, I'd be on my way to get my Nobel Prize. But sadly, I don't. Okay? Yeah, that's a great question. Okay? All right. So the Big Bang is science. Let's talk a little bit about the first couple of seconds after the Big Bang. By the way, this talk is listed as an hour and a half. I don't want to hold anyone hostage, so if you have to go in an hour, I will pause just in case anyone has to leave. Okay? I won't be offended, I promise. But I think we're due to end at 1, if not. Okay? So, we're going to talk in quite a bit of detail about the first 10 seconds of the universe. Now, the reason I have this diagram up again is that in the very, very, very early universe, the universe is extremely small. And so the things that are dominating the way the universe evolves in this very early stage are subatomic particles, also very small things. Okay? Well, as small as small can be. So we're going to be talking a little bit about particle physics, but as I say, if you want to hear more about particle physics just for its own sake, I'll be talking about that next week. Okay, so to start off with, T is 0. We can't think about T as 0. This is the Big Bang. So T here is the age of the universe, post-Big Bang. So 0, we can't do anything with. And in fact, even up to slightly later, this time of 10 to the minus 43, remember from our maths lesson at the start, this is 0.0000 with 43 zeros 1 seconds after the Big Bang. So very, very early. We call this epoch the Planck epoch. It's extremely short. I mean, giving it its own name is maybe a bit of a... Well, bit over complementary to it, but there's some interesting things happening here. So immediately after the Big Bang, we think that all of the fundamental forces of nature were unified as a single force. So in the universe as we see it today, there are four forces of nature. There's gravitational force, there's the electromagnetic force, which might sound like two. I'm saying electricity and magnetism, but really it is just one. And there are two nuclear forces. One that is responsible for holding the nucleus together, and one that is responsible for radioactivity. So there's a strong force, holds things together, and there's a weak force, weak nuclear force, that allows radioactive decay to happen. But in the very early universe, in this Planck epoch, we think that all four of these forces were unified as a single force, a so-called grand unified force. But again, I want to say as a disclaimer, this is so close to the start of the universe, to the Big Bang singularity, that everything we're talking about is very speculative. Okay? Now that doesn't mean I just made it up, but it means that we're testing our equations and our laws of physics to the extreme breaking point. Okay? So we have to take everything they tell us with a heavy pinch of salt. So these four particles here. Now, remember I said there are four fundamental forces? You might think, there's four particles here, so those are the four forces. But actually, no. This is one of the forces. The gluon gives us the strong force. The photon gives us the electromagnetic force. And then there are actually two for the weak nuclear force. The weak nuclear force is quite greedy. What's the missing one? Can anyone tell me? What's the missing one that's not represented by these particles?
Gravity.
No, the Higgs boson is something else. Gravity. Yeah, gravity is missing. So we don't actually have a particle description of gravity. Some people talk about gravitons as the particle that controls the gravitational force, but there are all sorts of problems associated with gravitons I'll talk about next week. Okay? So, four fundamental forces. The strong force, physicists are really bad at coming up with names, by the way. The strong force, as I said, it holds things together, so we call the particle that does it a gluon, because it glues things together. The photon is the particle that controls the electromagnetic force, so is responsible for all electricity, all of the behavior of magnets, and so on. And then these two down here control the weak nuclear force, which, as I say, is responsible for radioactivity. Okay? So, nuclear reactions and radioactivity. And then lastly, there's the gravitational force, which has no particle associated with it. We can think about gravitons, but as I say, these cause more problems than they actually solve. Okay? So, in the very early universe, we believe that all four of these forces were unified as a single force, a so-called grand unified force. But if we really want to study what this grand unified force is, we need the theory of quantum gravity, which we simply don't have. Okay?
Is that just an assumption, or is there a proof that it was a unified force?
It's a bit of an assumption, but what we know is that the four forces as they are today have been unified in other ways. So, for example, the electric and the weak force form the electro-weak force. We know that for a fact because in particle accelerators, when we crash protons together, we make such hot temperatures in a tiny little tiny little region of space that we sort of recreate the conditions of the very early universe. So we can study the universe up to about 10 to the minus 34 seconds, really sort of close, but not right the way back to this epoch. So we know that the electric and the weak force unify, and then we know that the electric and weak and the strong force unify. Now we can't study things further enough back to know that they all unify as one. So it's a bit of a sort of working assumption that the other ones unify, the electric and the weak unify, and then the electric, weak, and the strong unify, but the unification of gravity is not something we know how to do. Again, that's the problem of quantum gravity. It's the same problem, getting gravity to work with the other three forces. Any other questions at this point? Yeah?
It's fair to assume that the forces came from one original, but they differentiate further into smaller forces.
So the ones we've got today?
Yeah, it's fair to assume they differentiate further.
I hope not. I hope not. So there's, first of all, it would cause a lot more work for us to do, but second of all, So I'm going to talk about how these forces split off in a moment, and how we think specifically the electric and the weak force split off, just because this is what my PhD is in, so I know a bit more about this. And then, so I'm going to talk about that. Basically, as a preview, it happens by expanding bubbles at the speed of light. Again, I'll fill in more details on that later. But if the four forces we have now were to split in some way, the laws of physics would fundamentally change. So particle masses would change, the strengths of the various forces between particles would change, which would mean perhaps chemistry is no longer possible, which would mean perhaps biology is no longer possible, which would probably mean life is no longer possible. The universe would completely change its laws of physics in an instant. And we wouldn't see it coming because this change would happen at the speed of light, and your brains can't register something that hits you at the speed of light. Your atoms would just sort of disintegrate, and that would be about it, and we wouldn't know any different. So this is an idea called spontaneous vacuum decay, which is another thing to keep you up at night if you think about it too much. Okay, so slightly later on, so now we're looking 10 to the minus 43 to 10 to the minus 37 seconds. So again, remember this is 0.0043 zeros up to 0.0037 zeros after the Big Bang. Okay, so between these two periods of time, gravity separates from the other three fundamental forces. So this happens as what we call a phase transition. So very similar to how, if you freeze water, water turns to ice. This is a phase transition. You go from a liquid phase to a solid phase. Here we're going from a phase where the universe has one force, the grand unified force, to suddenly having two forces, gravity plus the other three bundled into one. Okay? And we call this bundled into one of the three, the strong, electromagnetic, and weak. We call this the electronuclear force. So this is sort of, to come back to your question from earlier, we know this happens. So we know that these two unify in this way. And we also know that these three split again into three separate forces later. So we are making a bit of a guess when we say they unify at this scale. But so far it's worked, so it probably will work again. It's the kind of logic you have to apply this close to the Big Bang. Okay. So, slightly later, so 10 to the minus 37 to about 10 to the minus 32. Now this is, even this late after the Big Bang, say late, this is still very, very early. This is still quite speculative, and not everybody is convinced that this period really occurred, although it's broadly accepted. At about this time here, I think I meant to write 10 to the minus 37 here, sorry, not 43. So between 10 to the minus 37 and 10 to the minus 32, we enter what's called the inflationary epoch. So this is where the universe expands extremely rapidly. So it grows exponentially in size. To put it into scale, it grows in this tiny fraction of a second by about 10 to the power of 24 times. So its width increases by a 1 followed by 24 zeros in this iota of a second. So again, putting that into perspective, that's like something expanding from the size of a grain of sand to the size of our entire galaxy. So this is the most rapid that the universe ever expands in its history. And this has a lot of consequences. So before inflation, the universe is still very small and still dominated by quantum mechanics, by the laws of physics that govern subatomic, very, very tiny things. But inflation happens so quickly and happens so rapidly that these quantum fluctuations that happen very, very early on in the universe are blown up to macroscopic scales. And it's thought that these sort of massively expanded quantum fluctuations will later form the seeds of galaxies and of stars and of other structures. Okay, this is maybe getting a little bit heavy. Do let me know if anyone gets a bit lost. I'm very happy to go back over something because we have got enough time. So, are there any questions at this point? Yeah.
How did you how did you define, or how was it discovered that it went from nearly 0 to 24 times. Yeah.
That's a brilliant question, and I'd intended to talk about that, so thank you for the reminder. So when we look at the universe, if I look at the part of the universe directly above our heads and the part of the universe directly below our heads, what's weird is that they look so similar. They look basically the same, and their temperatures are basically the same. Now, why is that odd? Well, it's odd because in order for two things to have the same temperature, they have to sort of be in contact with each other, okay? Because you know, it's like if you put an ice cube in a glass of water, it will reach the temperature of the glass of water. It'll bring the water temperature down a bit, and the ice will come up a bit, and they'll meet in the middle, and they'll reach thermal equilibrium. But now, two parts of the universe that are on opposite edges of where we're looking are so far apart. They're so far apart that even at the speed of light, they couldn't possibly have ever touched each other. Okay? Yet they have the same temperature. So how can that be? It means they must have been in contact later on than we thought they were in contact. Because at this point, no particles have yet formed. The universe is just a sort of extremely hot, energetic soup. There's no matter yet, it's all just energy. So before you can reach thermal equilibrium, you have to have you have to be a little bit later on in the evolution of the universe. So let me see, how do I put this? The fact that parts of the universe that are so far apart that even at the speed of light they could have never touched one another are still in thermal equilibrium, i.e. they must have at some point been touching each other, can only be resolved if in the very early universe they were touching each other and they were right on top of each other, and the universe just grew much quicker than it can possibly grow now. So they were touching each other, but it's just the universe grew so quickly, they're now further apart than you can possibly reach one another, that they were in contact in the early universe, which is why they have the same temperature. It's a tough argument to follow, actually.
I'm thinking of where you have like the playground where like universes or stuff is created in like the dust fields and stuff. It's still, I'm thinking of it in that way, like they were created in the same area, but they expanded since then. But they, like you say, they were still they started in the same place.
That's the idea. They had to have been in touch with one another in the very early universe. But if there's not a period of rapid inflation, even if they expand away from each other at the speed of light, they can't get to these opposite ends when we look up and when we look down to where they are now, because they're too far apart. The only way they could possibly have been in touch in the early universe is if they grew apart much quicker than we expected in this period of inflation.
Has the microwave background been produced yet? Has the microwave background that we observe in the sky?
No, not yet. Not yet. That's a bit later. Yeah, there's no photons yet. It's just complete soup. Any other questions? Or follow-ups? Yeah.
The early universe found that it expanded faster than the speed of light.
Yeah, that's a good question. So when I said nothing can travel faster than the speed of light, that's a bit of a lie. Nothing can travel faster than the speed of light locally. So, because for example, I know this is a bad example. At a given point in space, you can't measure anything traveling quicker than the speed of light. Okay, but the universe can expand quicker than the speed of light, because if you're considering two points separated by a very great distance in the universe, you can't make a local measurement of what's going on here and make a local measurement of what's going on here. The 2 points are in some sense disconnected, and so they can move away from each other quicker than the speed of light, because no one can sit in both places at once and say this one is moving faster than the speed of light, and so is this one. So you can't have two people agree that it's moving faster than the speed of light. So it's not locally you've got two things sat next to each other in one region of space. These two things can't move further apart from the speed of light, faster apart from the speed of light. But if they're separated by quite a large distance, they can, because it's no longer a local measurement. Again, that's quite a technical point. That's a hard one.
Each individual thing in between them is moving slower in the speed of light, but when you add them all together, it's faster.
Well, sort of, yeah. Locally, if you're zooming in on a single point, you can't measure anything faster than the speed of light. But if you're comparing two different points, that they can recede away from each other faster than the speed of light. But yeah, at a single point, you don't measure anything faster than the speed of light.
Is there a formula for this faster than the speed of light? Because the whole of physics we do today is in reference to the speed of light.
Yeah.
In terms of when we talk about space, we say that fast is a formula, another constant or whatever that we identified, or we don't have that.
So the Friedmann equation, the one I showed you before, this formula here predicts that parts of the universe can expand away from each other quicker than the speed of light. So this is something that comes from Einstein's theory of gravity. This is kind of not a new thing. This is something that emerged from Einstein's theory of gravity. That it's a local law.
We have a constant, like we have the speed of light.
No.
A constant. So it's something that no, it's faster than the speed of light.
But it can be anything.
Anything.
As fast as you like. Yeah. Not local.
Why? As fast as the universe.
As fast as the universe likes. Yeah, that's right. Any other questions?
Is that because that speed is so fast, the light can't possibly travel between these two objects for anyone to observe that light in between these two objects or something like that?
It's sort of like that, yeah. It's like two points that are different. You can't sort of simultaneously make a measurement of each point at the same time. And so you can't make a comparison of how fast apart they are moving, because you can't sort of know, well, I'm explaining this part quite badly. When you measure the speed of something, the restriction that it can only move less than the speed of light is a local restriction, meaning you have to be measuring the thing at that point in space, how fast it's moving. But if you've got two very distant points in space, there's no restriction that these 2 points move less than the speed of light away from each other.
Basically, it's like the flash, so you can't really point the flashlight at it because it's moved so fast. You can't point your light at it to actually notice that point. Or
yeah, you can sort of. I'm not. The truth is, it's a hard thing to explain.
Yeah,
It's something that's emergent in, if we were discussing the differential geometry of Einstein's field equation, you can see it in that, but it's a hard thing to explain verbally. When you get to a certain complexity in physics, the equations sort of lead you, by the hand, and it becomes harder to articulate necessarily the intuitive understanding of what's going on. I mean, if you come next week and when we're talking about quantum mechanics, this gets about 10 times worse, because we're going to be talking about things being in two places at the same time and define all sorts of things we see of, as concrete aspects of reality. So, yeah, to a certain level, to a certain extent, we have to let the maths guide us a little bit. But I appreciate it's frustrating if we're not talking about the maths as well. Okay? Yeah?
Within this inflationary period, the
Yeah.
cosmos has never moved so fast,
Yeah.
I think. But I thought the modern hypothesis that it's going to be topped out is speeding up.
Absolutely, that's actually right. So yeah, we will come to that, absolutely. So the universe is expanding, not only expanding, it's expanding at an accelerating rate, like you said. So, but at the moment the expansion is not, inflation is really fast expansion. So it's not yet that fast. I mean, if it continues to accelerate, it might get to that level of expansion. I'm not sure how long it would take.
maybe it stopped expanding at the fast speed we did in inflationary epoch,
Yeah.
whatever. At some point reached a peak,
That ended, yeah.
and then it's building up again to a fast speed, or
Well, so the thing is, the inflation, if you look at the time in which this happened, this
Yeah.
happened in, 10 to the minus
a split
37
of a
seconds.
split of a second.
Yeah, exactly. Whereas, of course, the universe has been accelerating in its expansion for the last tens of billions of years. So it's a much longer period. The diagram here sort of shows a little bit of what's going on. You've got the Big Bang here, and then this sort of white bit here where the size, boom, skyrockets up. That's inflation, where it grows extremely rapidly. This part here, you can see it's tailing off a little bit, so it's not just growing at a linear rate, it's growing at a sort of increasing rate. That's the current acceleration. Diagrammatically, that's what's going on. Okay? Yeah?
Sorry. The rapid expansion and then that slowing of that expansion,
Yeah.
is that the point at which your matter forms? So gravity is then having a slowing on the expansion of that?
Yeah, so the exit from inflation, I don't think I've talked much about this on the next slide. When inflation ends, this is when matter particles start to be created. So the energy from this field, this particle that causes inflation, we call it the inflaton, because again, we're not good at making up names, but all the energy from the inflaton is distributed into the standard model particles. And so we get matter coming from the leftover energy from this inflationary epoch. Yeah?
Is that the idea of why it stopped that rate of expansion then? Because the energy that was causing expansion has then just been put into matter instead?
It's more that the stop caused the matter. We don't quite know what caused the stop. There's something called the graceful exit problem in inflationary cosmology that basically just means we don't know why inflation ended, but it did, fortunately. But we don't know why. Okay. Okay, let's move on a little bit. So, so now moving on a little bit later to something we can say a few more concrete things about, but still with a lot of caveats. The electroweak epoch. So this is a slightly longer period of time, 10 to the minus 32 to 10 to the minus 12. Now, remember, we've skipped forwards a little bit, actually. We've skipped forwards a little. Remember, previously we had gravity and the three forces together as the electronuclear force. We've jumped forwards a little bit to where the electronuclear force has split into the electroweak and the nuclear force. Okay, so I've jumped a little bit, but I've only jumped about 10 to the minus 30 seconds. So, at the moment, the universe has three forces. It has the gravitational force, it has the strong force, and it has the electroweak force, which is the combination of the electric force, electromagnetic force, and the weak force. Okay? So every part of the universe is in this phase. But as I alluded to earlier, this will change, and it will change via a phase transition. And specifically, it will, we think, change via the growth of bubbles. So what we have in the universe, which I'm representing by this box, we have small sites where these little regions of space here begin to transition into a new phase. In the same way, again, if you've got a container full of water and you freeze it, it's not just the case that all the water suddenly freezes into ice and you've then got a container of ice. A little corner of the container starts to freeze, and the freezing sort of spreads out until it fills the container. And then you have a container full of ice. But it starts off in one little region, and then it grows, okay? So these regions here, we actually call nucleation sites, just like you would talk about the freezing of water. And these nucleation sites will grow. So within these bubbles, the electroweak force has split into two. It's split into the electromagnetic force and into the weak force. And as the bubbles grow, they will fill more and more and more of the universe until, now more of the universe has split into electromagnetic plus weak, and there's less and less of it, which is electroweak, the one force. And as they grow and as they overlap, eventually the transition completes, and all of the universe has transitioned into the four forces as we see today. Okay? So the way these bubbles grow, they grow at the speed of light. This is what I mentioned earlier when I mentioned, could the forces split again? Somebody asked. They could split again, and this is probably how they would do it with this transition via bubbles. So these bubbles grow at the speed of light. They start at a single point, potentially seeded by the presence of black holes or preceded by other structures, perhaps cosmic strings. We shouldn't get into cosmic strings, we'll get really sidetracked. But different things can seed where these nucleation sites begin, and eventually they grow and they fill the whole universe as we have it today. But if this happened again, if the forces split, the laws of nature would change, and again, we wouldn't see much about it. We would just have one of these bubbles of the new laws of nature appearing out of nowhere and coming towards us, and we wouldn't know anything about it. Our biology, our chemistry, our physics would change instantly, and we would probably stop existing. Okay? So now we reach the state of where the universe is today, more or less, There's still a lot more to happen, but we now have the 4 fundamental forces in place, okay, that we still have today. So the strong force, the electromagnetic force, the weak nuclear force, and the gravitational force. Okay, so also within this period, so during this phase transition, we have the first matter particles appear. So the first matter particles that appear are a mix of quarks and their antiparticles called antiquarks. Again, inventively named. So this process where matter forms, specifically what is called baryonic matter, which just means matter made of quarks, we call this process baryogenesis, where the matter we have in the universe today starts to come into being. Now, the laws of physics, although I said, antimatter is kind of like matter's evil twin, the laws of physics don't discriminate, and they treat matter and antimatter in basically the same way. We put them on an equal footing. As a result of that, when you create new stuff, create new matter, you should create the same amount of regular matter as you do antimatter. But if this happens, well, why is there any matter left? Because surely all of this matter and all of this antimatter, if they're created in equal proportions, should annihilate, as we discussed at the start. But a very small proportion is left over. Specifically, the amount left over is about 1 in 100 million. So about 100 million of these particles, only one will be left over. Now this imbalance, we don't know how to explain. Because again, the laws of nature say that they should be created precisely in equal proportions, and therefore should all annihilate and disappear, and there should be nothing left. We should just end up with energy. However, there's an imbalance. Something happened early on in the universe, perhaps due to the phase transition and the bubbles we were discussing, that meant this imbalance is preserved, and we end up with a bit of matter left over, whereas most of it is cancelled out by the antimatter. Okay? And again, this is a completely open question. We don't yet know how baryogenesis happens, how it happens that this imbalance occurs, and we're left with any matter at all. But it does happen, fortunately, or else we wouldn't be here. Okay? Any quick questions at this point? No? Okay. So we've got these matter particles. A few fractions of a second later, so now at about 10 to the minus 12 to 10 to the minus 6. So we're actually getting to reasonable numbers here. We're going from a trillionth of a second to a millionth of a second. The universe only contains quarks and the particles that stick quarks together, which remember we call gluons. So they exist in this extremely hot state, because the universe is very, very hot at this stage, as a quark-gluon plasma, where the particles sort of form a very hot soup where they start to peel away from each other. The quarks are not bound, they're sort of allowed to move freely. And as the universe cools, this sort of stops happening. They're not allowed to be as free as they were before. They start to sort of harden and freeze into more solid pieces of matter called hadrons. Okay, so hadrons, again, don't worry too much about the terminology, it's just lots of silly words physicists come up with, divided into two families that we call baryons, which are things made of 3 quarks, and mesons, which are things made of 2 quarks. Now, technically, a meson, one of the quarks has to be an antiquark, but again, we don't have to worry about that just yet. So they will harden and form the so-called composite particles. So this is matter made up of smaller pieces. So when I've been talking about the standard model here, all of these particles here are not made of any smaller pieces that we know of. You know, an electron just is an electron. You can't cut it up and see what's inside of it. Likewise, the quarks are just what they are. You can't cut them up and find out what's inside of them either. But these baryons and these mesons are made up of individual smaller pieces. They're made up of quarks. Okay. So we now have protons and neutrons. Because by the way, protons and neutrons are an example of baryons. They're things made up of 3 quarks. And now, with the sort of residual heat that came from this annihilation of the early baryon, we form equal amounts of positrons and electrons. Well, nearly equal amounts. Again, there is a sort of imbalance, which I've not drawn here, I should have drawn, where we form slightly more electrons than we do positrons, which is why we have some left over. They don't all completely cancel out. So this is called leptogenesis. And again, we don't know exactly why there are more matter particles left over than there were antimatter particles. We don't know why there is matter left. Because again, the laws of physics say they should be produced in equal numbers and would therefore cancel out and turn into just energy. Okay? So, after 10 seconds, this, by the way, this lepton epoch, leptogenesis, is happening between about 1 and 10 seconds. How old the universe is then. Okay? So after 1 second, we now have all the sort of basic ingredients that we need to make the matter we see on the Earth and in the solar system and what we see, again, in the galaxy. So we have protons, which is one kind of baryon, neutrons, another kind of baryon, and we have electrons, which is a kind of lepton. But it won't be till quite some time later, about 400 years later, that these things will stick together and form atoms as we know them. And then chemistry, begins. Okay? But, only 10 seconds into the age of the universe, all the stuff that will form all the matter we see in the stars, in the galaxies, has been formed. Okay? All the individual components are there. Okay? And we're going to talk more about what I haven't mentioned here, which is dark matter. We will talk about next week. Okay? So when I say all the stuff we can see, that's the crucial part. It turns out that actually the stuff we've described here, the stuff that is made out of atoms, protons, neutrons, and electrons, only counts for 5% of all the stuff in the universe. 95% of it is completely invisible. You can't see it, you can't touch it. There's some of it in this room right now, and it fills the galaxy and holds it together. Okay? I promise. I'm not talking rubbish. Okay? But we know not much more about it than that. Okay? So here I've just put up a very sort of short timeline of some of the key events that happened after the first 10 seconds of the universe. So about 400,000 years after, we have the formation of the first atoms I just showed you. About 200 million years, we have the first stars. 300 billion, the first sort of proto-galaxies forming. And then about 1 billion years, the first stars in our galaxy, so in our Milky Way, the inner part of the Milky Way, begin to form. About 9 billion, 231 million, and 800,000 years after the Big Bang, our sun is born. And then about 9 billion, 257, so about 26 or so million years later, our Earth forms. And then a handful of billions of years after that, so when the universe is about 10 billion, 400 million years, we believe life emerges sometime before that. Okay? So, quite a lot happens quite early on, but a lot of interesting stuff happens significantly later. Okay, so I want to talk a little bit about our cosmic address, but actually I don't think I'm going to be able to get through all of this. So I also promised I would give time if anyone wanted to leave. So we've got another 15 minutes, but maybe let's do a couple of questions now. And if anyone has to leave, if you weren't expecting it to be an hour and a half, that's all good too. So any questions? Yeah?
When you were showing the information a second ago about the 10 seconds and then it jumped to the 400,000, is there nothing that we know that happened in that? Because it's such a big jump.
There's quite a lot. There's a whole...
There is other stuff that happens in that.
Yeah, there's a part where dark energy dominates. There's a part where the dominant form of energy in the universe is in the form of photons, where we have a lot of annihilation of the various matter and antimatter. There's a lot going on. Okay. Yeah, it's just that's good.
Sorry.
No, that's fine. Yeah.
So, in your opinion, what is kind of the most interesting research that's going on at the moment in this kind of space of primitive cosmology? Like, where are we investigating at the moment?
Well, I'm highly biased towards my own research. So my research looks at the, broadly speaking, it looks at the electroweak phase transition, but it does so by looking at models of the universe which might include higher dimensions. So I generally deal with models that have about 5 dimensions as opposed to the usual 4. By the way, the fourth one is time, so this is one extra space and time. To try and understand how these bubbles form and how they collide and what they do. Because one thing these bubbles do, if they do form when the universe transitions, when they collide, they should release gravitational waves. So they should make ripples in space, which, if we can detect them, would tell us a lot about the early universe. So, yeah, some things I'm particularly excited about are the detection of gravitational waves coming from either the exit from inflation or from the electroweak phase transition, if this does happen by bubbles. But as I say, I'm highly biased. Yeah.
I suppose that gravity makes a bit more sense when you introduce higher dimensions like the ring theory and things like that. Do you think that's the case?
Yeah, so the best quantum theory of gravity we have is called string theory. This, again, is very simple. It posits that all matter in the universe is made of one-dimensional vibrating strings in an 11-dimensional space-time background. Just easy stuff. I'm kidding, it's extremely difficult. It's not my area of expertise. But it solves a lot of problems. The issue is that, in a way, string theory is too smart for its own good, because there's so many degrees of freedom that it describes a quantum theory of gravity, but does it describe the quantum theory of gravity in our universe? Well, it might describe very many different quantum theories of gravity, but what it can't do is reproduce, the different particles we have in our universe, the forces correctly. So we haven't found the right string theory, but even so, there are some issues at very high energies that are not tackled by it. Alternate theories are generally less popular, but there's something called loop quantum gravity that tries to do the same thing in a different way, generally less successfully. But yeah, string theory is exciting. It's something that occurs at such high energies, so close, in cosmological terms, so close to the Big Bang that we can't reproduce them in particle accelerators. So it's nothing we can test. It's very difficult to even call it science in some respects because there's no testability there. Okay. Yeah.
Sorry to go right back to the primeval atom.
Okay.
I didn't have a chance to ask this question earlier.
Mm-hmm.
What baffles me is what made the primeval atom explode in the first place? I mean, the scientists deduced this because it suits what's happened to the universe to start?
Yeah, so the primeval atom is the Big Bang, basically. It's the Big Bang singularity. Just this is what George Lemaitre called it. We now call it the Big Bang, but it's the same idea. And as I say, we can't take the laws of physics back to the Big Bang. The moment of the Big Bang itself is it's completely opaque to us. The laws of physics won't go far enough back to study it. What we do know is that the universe is expanding currently, and by studying it at very high temperatures in particle accelerators, we've reproduced some of the conditions a short time after the Big Bang. But the Big Bang itself, we can't study. In the same way we can't study the singularity at the center of a black hole. It's the same mathematical problem.
The cause couldn't be ascertained then?
No, we can't go beyond it. Yeah, we can't go back to beyond the Big Bang. There are some theories that treat the Big Bang as potentially occurring due to some sort of earlier inflation. Again, they're not really supported, and again, it's quite hard to falsify them. There's theories are a sort of dime a dozen.
If the universe collapses in the future,
yeah.
There'll be another Big Bang, basically.
Yeah, big bounce. That's what this is sometimes called. There could be. And again, there are models that suggest this, but it's very hard to say. Any other questions? Yeah?
All these eras and epochs that we've talked about up to now, they happened before a visible light, yeah? Yes, the one so far. Yeah. How can we calculate the time of these expansions and things when there was no measure?
So the time basically correlates directly to energy. We kind of know how hot the universe was at different times. And it then becomes a question of particle physics more than cosmology. Because particle physicists, we write equations and have models to explain what the different particles are doing at certain temperatures. So what we're really doing is I'm not actually calculating what the universe is doing 10 to the minus 32 seconds. I'm calculating what it's doing at, say, a billion GeV of temperature, which is a unit of temperature. Okay. So we're doing those calculations instead. So,
Do you know how long these changes in temperature? Do you know how long the time was in between these changes?
roughly, roughly we know the time scale. I mean, it's more that we can describe what's going on at certain temperatures, and then we're loosely translating those temperatures to times. So it would be more accurate if I was saying at a temperature of a billion degrees, this is what's going on.
Yes.
But we translate it to times to make it make a bit more sense to understand how it fits into the timeline. Okay.
So it's manipulation of physics.
Exactly. Yep.
So you've kind of made reference to how string theory kind of isn't really science because it doesn't have that kind of testability aspect. And you kind of made reference to like particle accelerators, etc. Like, what are the tools that we're using currently to kind of do this science?
So the tool we use is the same tool we've had basically for the last 70 years, which is called quantum field theory. So it comes from quantum mechanics. It's the fusion of quantum theory with Einstein's special theory of relativity. The general theory we can't bring in yet. This is the quantum gravity problem. But the special theory and quantum mechanics go together quite nicely. And this tells us all the different ways that photons and electrons interact. It tells us how quarks stick together via gluons. And it allows us to look at what's happening at higher temperatures. I mean, it's difficult. You have to do a lot of. You can't just solve the equation like you would in algebra in school. We have to use a lot of sophisticated techniques, Feynman diagrams, and doing computational things, supercomputers, lattice QCD, all sorts of crazy things. But yeah, it's the same basic tool we've had for the last 70 years, which is quantum theory plus special relativity. Okay. Any? Yeah.
So when we're talking about like when they use the photons to try to observe that like the Large Hadron Collider, so you said they can only observe, was it like 10 to the negative 37?
Something like that. Yeah.
So what's preventing them from is it just not having a way to measure it?
We've got to smash them together harder. So the Large Hadron Collider is pretty big. I can't remember the exact diameter, but it's it's a couple of miles in diameter. If you want to get to higher energies, you need one that's even bigger. And that takes a lot of money, and that takes politicians who are interested in fundamental physics and the Big Bang, which is not a very common preoccupation of politicians. So we just don't have the money to build a bigger one. A bigger one would be great. The US government nearly built a super collider in the 1980s, but Republican senators sadly trashed that. So it's a funding issue mainly. But then again, we can't just throw money at it and say, oh, we just need a bigger collider, we'll see if anything comes out. Because actually not that much came out other than the Higgs boson at the Large Hadron Collider. I mean, I say other than the Higgs boson, that's still a pretty big deal, but we were expecting potentially signs of supersymmetry, extra dimensions, and none of it came to light in the end. Okay. Any other last minute questions? Yeah.
I'll go back to what the other lady said in terms of years versus temperature.
Yeah.
Basically. But is it, do we actually know, when we say 9 billion after our sun, we actually measure the temperature, and that's how we assume it was 9 billion years, yeah? Well, how do we know it's 9 billion to that, associated to that temperature that happened when the sun appeared?
Well, so the temperature energy thing is more about the early universe. When we're talking about later times, like 9 billion years when the sun forms, then we're doing cosmology and astrophysics.
So how do we measure that based on, how do we know it's 9 billion and not 15 billion years? I mean, yeah. I mean, I get it's 9 billion. And
yeah.
Yeah, how do we age?
How do we age the sun? Well, we have models of how long stars live based on their masses. So I would guess, given that we can measure the composition of the sun, I don't know, by the way, I'm not exactly sure how we date the sun, but I would guess as stars age, their metallicity changes. The composition of whether they're mostly hydrogen and helium or whether they have heavier metals in them changes. So I would guess we can measure how much of these heavier atoms are inside of the sun based on, we know how heavy the sun is as well. That's a different question, how do we know how heavy the sun is? But we can then see how long we expect the sun to stay in its current phase of evolution, the main sequence phase. And then by comparing it with other stars, we can see, given it has this many metals within it, it's probably 20% into its main sequence phase, which we expect to last so many billions of years. Therefore, it's probably about 4-point-something billion years old. That's all I get. Then they're happy with that.
No.
Okay.
I have to say,
Sorry. Well, it's quite intelligent guessing, but yeah.
Billions, trillions. Why are we not saying trillions? Why are we saying billions? I mean, these measures in time
Yeah.
are so huge.
Yeah.
And we do a lot of guessing we can be so wrong about. And it
Well,
can
but
actually be 10 minus whatever plus 3 trillion years when the sun appears rather than 9 billion.
Well, but we know the universe
How do
is.
we know that exact billions rather than trillions or millions?
Well, we know the universe is about 13.8 billion years old.
Based on what?
Based on the information of the recession of the galaxies, tracing it back, comparing it with some modelling from Friedman's equations. We know that the sun, of course, can't be 1 trillion years old if the universe is only 1 billion years old. To a certain extent, yeah, science is about using models, and we have to make assumptions. Like, we have to assume the laws of physics here today are about the same as they were in the past. But unless we have any reason to believe they were different, we have no reason to really consider that seriously. It's like Occam's razor. You take the whatever proposal has the fewest number of initial assumptions is probably the correct one. So it's more minimal to assume that the laws of physics are the same now as they were several billion years ago. And if we trace it back, we find that it should be about 13.8 billion years ago that the Big Bang occurred. And if we compare the metallicity of our sun with other stars, we see that it's probably about 4 and a bit billion years old. You might be off by a couple of million, but order of magnitude, it's in the few billion, and the universe is in the tens of billions years old. And we update it. If we make errors, we change them. Okay. Okay. We run out of time. Well, let me, as you can see, there was quite a lot to talk about. Let me see, I guess, well, maybe I will cram some of these into next week. Let me just end by plugging, next week we're going to talk about particle physics here in the same room at the same time. Then the week after that we're going to talk about time travel, so Einstein's special theory of relativity, and then come back to black holes the week after. And if you want to see, I have uploaded these notes onto my website URL, you can see there. So you can take a look at all the slides I just flicked through very quickly if you want to. Okay? Well, I think we'll have to leave it there. Thank you very much. Thank you.